Welcome to the concluding lecture on atropine, part 2nd. The contents of this lecture are structure elucidation of tropine, which is a part of atropine, synthesis of tropine, and finally the synthesis of atropine. This is the tropine molecule. You can say it is a bicyclic compound, alcohol with N-methyl group present. It is known as tropine. We will elucidate the structure of tropine. The structure elucidation of tropine. It is based on classical method, chemical analysis. First step is the molecular formula. On the basis of elemental analysis and molecular weight determination, the molecular formula is C8H15NO. The second step is the degree of unsaturation present in tropine. It is given by double bond equivalence, which is given by the formula A minus B by 2 plus C by 2 plus 1, where A represents the number of carbon atoms, 8. B represents the number of hydrogen atoms, it is 15, and C represents the number of nitrogen atoms, it is 1 plus 1. Substituting the values, we get double bond equivalence equal to 2. This means that either 2 double bonds or 2 rings or 1 double bond or a ring is present. The next step is to determine the nature of unsaturation. It is given by the following reactions with bare reagents and bromine water. Both these reagents, tropine showed a negative test, which means that olefinic double bonds are absent in tropine, and tropine is a saturated molecule. So the double bond equivalence corresponding to 2 means 2 rings may be present in tropine. Nature of nitrogen atom. As there is one nitrogen atom, we have to determine the nature of this nitrogen atom. Tropine consumes one molecule of methyl iodide to form quaternary ammonium salt, which means that the nitrogen atom present in tropine is of tertiary nature. Next step is the presence of N-methyl group. When atropine or tropine is treated with the hydrogen iodide at around 150 to 300 degrees centigrade under pressure, one molecule of HI, it gives out one molecule of methyl iodine, which when subtreated with silver nitrate in the presence of ethanol, it precipitates out in the presence out as silver iodide. The quantitative estimation of this silver iodide determines the presence of N-methyl group in tropine. This method is known as Herzig-Meyer method. Next point is the Koh Fusion, which also determines the presence of N-methyl group. Tropine forms methylamine on fusion with KOH, which means that N-methyl group is present in tropine. Next step is the nature of oxygen atom, which is present in tropine. As tropine contains one oxygen atom, what is the functionality of this oxygen atom? It is determined by the chemical reaction. On atropine, on treatment with carboxylic acid, it forms an ester, which means that hydroxyl group is present in tropine. There is one more reaction on oxidation. On oxidation, tropine forms ketone, which means the nature of this hydroxyl group is of secondary, means secondary hydroxyl group is present. Next step is the detection of basic skeleton. This basic skeleton is the oxidation method or oxidative degradation method, which determines the nature of skeleton present in the tropine. Tropine, this is Kuhn-Roth oxidation. Tropine on treatment with chromic acid, it forms tropinone. As you can see, number of carbon atoms in tropine and tropinone is the same. Hydrogen atoms, 2 hydrogen atoms are less in tropinone, and nitrogen and oxygen are the same. This oxidation, there is nothing but the hydroxyl group, secondary hydroxyl group which is present, is converted into carbonyl group. Means secondary alcohol on oxidation forms ketone. This is the inference drawn from this reaction. This tropinone on further oxidation, it forms tropinic acid. As you can see, the molecular formula is C8H13 and oxygen atoms has become 4 oxygen atoms. This means this tropinic acid is a dicarboxylic acid. Means this oxidation, degradative oxidation has taken place, opening the ring and converting into dicarboxylic acid. COOH and COOH is there. On this tropinic acid, on further oxidation, it forms a compound of known structure N-methylsuccinimide. N-methylsuccinimide. This is the final product of Kuhn-Roth oxidation. The inference is drawn from the formation of N-methylsuccinimide is the presence of 5-membered pyrrolidine ring in tropinic acid. 5-membered, 1, 2, 3, 4, 5. This is 5-membered pyrrolidine ring is present, and also a methyl group is present in nitrogen atom. These two inferences are drawn with this oxidative product. Secondly, tropinic acid when subjected to Hofmann's exhaustive methylation, we get an unsaturated acid. Scientists got an unsaturated acid which is known as piperidine carboxylic acid with the formula C7H8O4. This Hofmann's exhaustive methylation has expelled out the nitrogen atom from the compound, from the tropinic acid, and yielding the unsaturated acid piperidine carboxylic acid. This piperidine carboxylic acid, on further reduction, it forms pimilic acid. The structure of pimilic acid is also known, and it contains 1, 2, 3, 4, 5, 6, 7-membered. Pimilic acid is a 7-membered structure. This means that in tropinic acid or in tropine, it contains a 1, 2, 3, 4, 5, 6, 7-membered ring is present. Formation of pimilic acid suggests a 7-carbon chain in tropine. Again, you can see a flow chart of this. Tropine, Kuhn-Roth oxidation, chromic acid and sulfonic acid. Final product is a known compound N-methylsuccinimide, which proves the 5-membered ring is present here with nitrogen, and methyl group is present on nitrogen, and this 5-membered ring is the reduced ring, means saturated ring is present, pyrrolidine ring. Tropine, when subjected to KMnO4 oxidation, it forms tropinic acid, which is a dicarboxylic acid. This tropinic acid, when subjected to Hofmann's exhaustive methylation twice, This is the first part of Hoffman's exhaustive methylation. Reagents, as we already studied, methyl iodide NaOH, converting this tropinic acid tertiary nitrogen into quaternary salt. Then the quaternary iodide is formed. Then when it is treated with silver oxide, corresponding hydroxide is obtained, and on heating and reduction we get an unsaturated acid, and the nitrogen is expelled out from the ring. It is then subjected to second step of the Hoffman's exhaustive methylation twice. Tropinic acid is subjected to twice, converting it into an unsaturated acid. This means when exhaustive methylation is done twice, this means a bicyclic ring is present in tropinic acid. This on reduction, it forms finally a pimilic acid, which is a 7-membered ring. This means that tropine contains a 7 and a 5-membered ring. And nitrogen, as you can see the molecular formula of nitrogen, there is only one nitrogen atom. This means this N-methyl group is common in both the rings. The next step is the detection of the basic skeleton. This is formation of cycloheptane, another series of chemical reaction for the degradation method. Propene, when treated with sulfuric acid, dehydration takes place, converting it into tropidine, C8H13, and means a molecule of water has been removed. Dehydrated product is tropidine. This tropidine, when subjected to Hoffman's exhaustive methylation, we get tropylidine. This and nitrogen is being expelled out with one methyl group also, converting it into C7H8. This tropylidine on reduction forms a cyclic compound cycloheptane of known structure, which is a 7-membered ring. The next series of chemical reactions for the detection of basic skeleton is tropine. When subjected or when reacted with HI, it forms tropine iodide. This means hydroxyl group which is present. The nucleophilic substitution took place, and removing the OH and the replacement or substitution with iodide took place, resulting in the formation of tropine iodide, C8H14 and I. On further reduction, it forms tropane with the formula C8H15N, which on zinc dust distillation, it gave a compound of known structure, which is 2-ethylpyridine. This 2-ethylpyridine, this gives an important conclusion that the reduced pyridine ring or piperidine ring is present in the basic skeleton of tropine. So tropine contains only one nitrogen atom, so it is common to both the rings, and this nitrogen must also contain an methyl group also is attached to this. So we can propose the structure of this tropine. You see 1.1, 2, 3, 4, 5 this ring, and 1, 2, 3, 4, 5, 6, 7. 7-membered ring and 5-membered ring with an methyl group common. When we superimpose both these things, we get this type of bicyclic ring. As you can see, 1, 2, 3, 4, 5, 6, 7-membered, and here it is 5-membered ring with an methyl group common. So this is the Will-Strater structure for tropine. This structure was given by Will-Strater. We have to substitute one hydroxyl group also, secondary hydroxyl group, as we know that this tropine is optically inactive. So if we substitute this on these two carbon atoms, this won't do. This is the symmetry axis present in tropine. This is the symmetry axis present in tropine. So if hydroxyl group is present at this carbon atom, then it will render it optically inactive. So the position of the secondary alcoholic group is about this symmetry element. So this is the probable structure given by Willstatter, which explains some of the reactions which we have studied earlier. As you can see, this is the probable structure or Willstatter structure for tropine. When subjected to chromic oxide, it forms Kunroth oxidation, it forms tropinone, which on further oxidation, degradation, it forms dicarboxylic acid. As you can see, this dicarboxylic acid, this degradation has taken place, resulting in the opening of this ring and converting it into dicarboxylic ring. Means this bicyclic ring, one ring has opened or degraded, converting it into a dicarboxylic acid, which is tropinic acid, which on further oxidation it forms N-methyl succin imide structure, which is pyrrolidine structure with N and methyl group. So this final product, N-methyl succin imide of Kunroth oxidation, has been justified with this Willstatter structure. Another set of reaction, as we can see, when treated with tropine, when treated with HI, nucleophilic substitution of OH took place and converting it into tropine iodide, which on reduction forms tropane. You can see iodide has replaced by N, and methyl group iodide has been replaced by H, reduction converting it into tropane, which on zinc dust distillation it converts into a well-known compound 2-ethylpyridine. This 2-ethylpyridine, this means that the piperidine ring is present in tropane. Thus the formation of 2-ethylpyridine is explained by this Willstatter structure. Finally, the structure of tropine is confirmed by its synthesis, which was given by the scientist Robinson. He has an outstanding work. He has done outstanding work on alkaloids, and for which he was awarded Nobel Prize for Chemistry in the year 1947 for his work on alkaloids. And he took a very simple compounds, industrially feasible compounds, for the formation of this tropine structure in simple steps. As you can see the structure of tropine, he degraded the product into three parts. First part is the, as you can see here, succin aldehyde, CH2, CH2, CHO. So the first substrate which you took was the succin aldehyde. Secondly, you can see here this simple degradation product is methylamine, methyl CH3 and H2. He took methylamine, the second reagent. And the third one is the acetone, CH3CO CH3. He took, instead of acetone, he took calcium acetone dicarboxylate. Means he took a dicarboxylic acid of acetone, or the calcium salt of dicarboxylic acetone dicarboxylate, or in other it is also glutaric acid, calcium salt of glutaric acid. This is, our other name is calcium acetone dicarboxylate. He took this compound instead of acetone because to increase the yield of tropine, because you can see this CH2 groups, this carbonyl group is flanked by two methylene groups, reactive methylene groups, and with these reactive methylene groups are joined by the carboxylic group, as you can see, rendering it more effective. These three reactions, these three reactants, they reacted with a double Mannich reaction, 2 times a Mannich reaction. As you can see, oxygen, hydrogen, and here methylene group. This hydrogen, here water, a molecule of water was eliminated from this, and the second succinylate, second Mannich reaction, H, hydrogen, oxygen, and this second methylene group reacted, means double Mannich reaction yielded this intermediate compound, which on decarboxylation or heating decarboxylation took place, converting it into tropinone, and tropinone on reduction with zinc and hydrogen iodide yielded tropene. So by 2 or 3 simple steps we got tropene as our product. So this is Robinson synthesis, simple synthesis yielding our product. So the structure of tropene is confirmed by this synthesis. Our last step is the synthesis of atropine. Atropine is the compound which is ester, tropene ester of tropic acid. So the reagents which we took is the tropene plus tropic acid, Fischer esterification in the presence of mineral acid, and we get, on esterification we get atropine. So with the help of simple chemical reactions of organic chemistry and with some logical thinking also, the scientists have determined the structure of atropine. So by applying this simple reactions or classical method, we can easily determine the reaction or the structure of or structure elucidation of simple alkaloids also. I hope you would have understood the chemistry dealt with this. Thank you.